Mina Aganagic, and we'll talk about knots, mirror symmetry, and the model.
Okay, I want to thank the organizers for inviting me and for bringing us all here together. So, quantum physics has played a central role in knot theory for a very long time. This goes back to Witten's work in '88, or perhaps even earlier. Witten showed that the Jones polynomial, one of the best-known knot invariants, is computed by SU2 Transimus path integral on S3 with a line operator inserted along the knot and colored in fundamental two-dimensional representation. So one gets more quantum knot invariants by varying the representation in the gauge group. You get finer invariants yet by a kind of roughly second quantization, where one interprets Transimus knot invariants as dimensions of Hilbert spaces of yet another theory. That's part of the categorification program in knot homology. Now, what I'll show you today is that by embedding Transimus theory into topological string, one finds that string duality suggests that, in fact, classical geometry may play the central role in answering the basic question in knot theory, when are two knots distinct? Okay, so the embedding of Transimus theory into topological string, what this gives you is an action of two string dualities, the large N duality and Strominger, Yau, and Zaslow mirror symmetry. And taken together, they suggest that there should be a reformulation where quantum Transimus knot invariants arise by quantization of a classical geometry associated to the knot. Now, to be precise, this requires a generalization of Strominger, Yau, and Zaslow mirror symmetry. And I will first explain what the generalization is, and then explain what it has to do with knot theory. And finally, I'll explain yet another dual viewpoint on the whole problem, which should be very, very powerful, and which we call the D model. Now, this is joint work with Kumran Vafa and also with Tobias Ekholm, Lenny Eng, and Kumran. Okay, so Strominger, Yau, and Zaslow conjectured that for every compact Calabi-Yau manifold, X, with a mirror Y, that every compact Calabi-Yau manifold admits a family of special Lagrangian T3s, such that the moduli space of a brane wrapping the T3 in X is the same as the mirror Y. However, once one includes disk instanton corrections. And so here's a 3 brane wrapping the T3 fiber of X and the dual brane, which is just a point brane, on the mirror. So this way, the classical moduli space of this point brane on the mirror and the disk instanton corrected moduli space of this 3 brane probing X are the same. Okay. Now, on a local toric Calabi-Yau manifold, it's known that such special Lagrangian T3 fibration does not, in fact, exist. And instead, you get the mirror by considering a special Lagrangian of topology of R2 times S1. Now, the moduli space of a special Lagrangian wrapping R2 times S1 of an A brane on this is one complex dimensional. This follows from a theorem by MacLean, which says that the complex dimension of moduli space of a special Lagrangian 3 cycle is B1 of L. So the real dimension is B1 of L, and this gets paired up with the modulo of the flat U1 bundle, so you get one complex dimensional manifold. Now, the fact that for these local toric Calabi-Yaus, that probe A brane has topology of R2 times S1, and with it one complex dimensional moduli space, is connected with the fact that the mirrors of these manifolds are captured by Riemann surfaces. In 2000, Hori and Vafa showed that the mirror of any toric Calabi-Yau is a hypersurface in C4 of this form. And you can see here that all the geometry of the mirror is captured in a Riemann surface, sigma. Okay. On this Calabi-Yau, there is a canonical B-brane whose moduli space is this Riemann surface that captures the geometry. You get this B-brane by setting, for example, v is equal to 0 and choosing a point on the Riemann surface. So you get a curve parameterized by u, whose moduli space is this Riemann surface. We can call it the mirror Riemann surface because it knows all about the mirror. And that canonical brane is analogous to a point brane on a compact Calabi-Yau. It's a brane whose moduli space captures the geometry. Classical moduli space captures the geometry. Okay, so in the B model, everything is classical. Now, this canonical B brane turns out to be mirrored to a special Lagrangian brane on the Tar Calabi-Yau X, which is also canonical and of topology of R2 times S1. I don't want to describe what this brane is, but if you open, say, the very first paper on the subject where special Lagrangians were defined by Harvey and Lawson, cousins of these branes were written down there, and then they were studied later by Joyce. So it's sort of the first thing you can think of. It's very canonical. Analogous to the T3 fiber, I guess. Okay, now this Riemann surface, which is the classical moduli space of this canonical B brane on Y, is also the disk instanton corrected moduli space of this mirror canonical A brane. Okay, so what do you mean by that? So for a special Lagrangian A brane with B1 is 1, the classical moduli space is locally parameterized by x, it's a complex variable x, whose real part is the area of a disk ending on L. The exact moduli space turns out to be a Riemann surface. And this Riemann surface is generated by the A model Gromov-Witten disk amplitude, which is a function of x, of the size of the disk, as a set of points p and x related like that. Okay. Now, the Gromov-Witten potential on the disk counts the number of holomorphic disks ending on L, and classically it vanishes. So classically, the moduli space of a brane, P is just dW, is 0. So the moduli space is classically just P is equal to 0, so you just get all of the x-plane, and that's it. However, once you include instanton correction, the story changes. You get a more complicated Riemann surface. And that's the quantum moduli space. Now, suppose that you can find more than one mirror brane of the, so more than one Lagrangian brane of topology of R2 times S1. Then these different branes would generically see the geometry of the manifold is started with differently. And so you would get more than one mirror by studying the quantum moduli space of these branes. Namely, for branes wrapping different Lagrangians of R2 times S1, of topology of R2 times S1, you'd get a different disk amplitude, and with it, the different classical moduli space, and hence a different mirror. Now, what I'll show now is that, in fact, this happens. If you study Calabi-Yau, which is, it's a conifold, the O-1 plus O-1 bundle of a P1, so it's conifold with S2. There is, in fact, one such brane for every knot in S3. And every such brane would then, by this generalization of SYZ, lead to a new mirror depending on the knot. Well, okay, so how do you construct such branes? So a way to construct them is using a geometric transition. So this is the manifold where we want to study the branes in, this conifold with a P1. And so you shrink the P1 and grow the S3. This is a conifold transition. Now, it turns out that it's easy to construct branes here and then push them back through the transition. So here's how it works. On T star S3, for every knot in S3, you take the knot together with its conormal bundle. So you get a special Lagrangian of topology of R2 times S1. Okay.
Do you mean special Lagrangian or just Lagrangian?
You get a Lagrangian whose, I guess, Maslov index vanishes. So there should be a special Lagrangian somewhere in it. In there.
I think that you get a special Lagrangian, it's not the Aganagic, which you will.
Well, one is not interested, like for Calabi-Yau manifolds, you're not really interested in some Calabi-Yau metric that you can write down. You know, you're just interested in existence of a metric. Okay. Okay, so starting with this special Lagrangian, that you construct here. Now, I started with the knots in S3 plus the two directions sort of orthogonal to it, because its topology is R2 times S1. It has one-dimensional moduli space, which you can use to lift the brane off the Lagrangian off the S3 and then just push it through the transition. So this way, you get a special Lagrangian on X, where you want to study them, of the topology of R2 times S1. And presumably with it, a new mirror of X. So in this way, mirror symmetry for this class of Calabi-Yaus gets related to knot theory. And this connection goes beyond just constructing knot invariants, it goes beyond just constructing Lagrangians, as is well known, and I'll explain. Now, there's a conjecture. This Calabi-Yau conifold, which we studied, has a deep connection with knot theory to begin with, which goes as follows. So, Gromov-Witten theory on this conifold with an S2. So is related to Transheimer's theory in S3, and if you consider a conifold on S2, a conifold with S2 with this Lagrangian, this gets related to Transheimer's theory in S3 with considering Transheimer's knot invariance of the knot K. So how does this work? So Gopakumar and Vafa conjectured in '98 that there's a large N duality, what physicists call large N duality, that relates the topological A model on this, on X with an S2 and an X and a T star S3, where the size of the P1 is N times lambda. And on the other side, after the transition on the S3 side, you get N A branes on the S3. So the number of branes on the S3 gets related to the size of this P1. And so this geometric transition, which we so far used as a tool to constructing special Lagrangians, is in fact a duality. Okay? Now, it's a duality which actually gets related to Transheimer's theory, namely the A model on this cotangent space of S3 is in fact, with N A branes on the S3, is in fact the same as SU and Transheimer's theory on S3. And that's the result of Witten from '93. So the reason this comes about is that A model it's counting holomorphic maps. With branes, it's counting holomorphic maps with boundaries. And if your geometry is T star S3 and with boundaries on the S3, all such maps are degenerate because there are no finite holomorphic curves. And so what the maps degenerate to is Feynman graphs of Transheimer's theory on S3. When you're studying topological string, you're studying not just holomorphic maps, but you also vary over the moduli space of the base curve. And what this says is that only boundaries of the moduli space contribute, where everything localizes to graphs, Feynman graphs of Transheimer's theory. So the A model string theory in this background is the same as Transheimer's theory on S3. Now, Auguri and Vafa explained that if you study this cotangent space to the S3 and you introduce these additional Lagrangians co-normal to the knot, that this corresponds to studying Chern-Simons knot invariants of the knot K. Okay. Okay. And so all of this, as I said before, gets related by a geometric transition to, which is now a duality, to studying branes on conifold with a P1 together with of this, which are co-normal to the knot. Okay. Okay. So so this large N duality, and more precisely, it relates computing Gromov-Witten invariants in the setting to Chern-Simons invariants of the knot. And just to remind you again, the rank of Chern-Simons gauge group is encoded in the parameter that keeps track of the degree of the maps to the P1. And lambda here is the effective coupling constant that keeps track of the genus, and it's the same on both sides. Okay, so the geometric transition allows one not only to construct Lagrangians, but also to compute their amplitudes. These Lagrangians are known for a long time, but nobody managed so far, other than in some very simple cases of unknots and Hopflings and so forth, to actually compute their Gromov-Witten theory, turn Gromov-Witten theory on the space into a computation. So now what we are interested in is finding the Gromov-Witten potential on the disk for the branes in X. And while we would have liked to solve this problem down here, at the moment we can't, not directly in Gromov-Witten theory. So instead, we'll use Chern-Simons theory and this duality to get the Gromov-Witten potential of this brane in X. And with it, from it, we can construct the geometry of the mirror. Okay. So more precisely, as Auguri and Vafa explained, if you're interested just in studying a single brane on the Lagrangian, this turns into a question, and you want to know everything about it, its entire Gromov-Witten theory, all genus, any number of holes. What this turns into is computation of Helmsley polynomial colored by totally symmetric representation. But you need to know them all. Okay? So the exact partition function of a single A brane in X is sort of a discrete Fourier transform of the Helmsley polynomial in totally symmetric representation. Okay? So starting with this, the duality conjectures, large N duality, would tell you that expanding this in powers of lambda, you get Gromov-Witten invariance. Okay? And in particular, if you're just interested in the disk amplitude, you just take the leading piece of this in the small lambda expansion. So knowledge of the Helmsley's totally symmetric representations, a small piece of it is the disk amplitude, a very small piece, because you're taking the limit where you just keep the leading piece. Okay, so in this somewhat roundabout way, you can recover the Gromov-Witten potential of the A brane on this Lagrangians of topology of R2 times S1, one for each knot. The Lagrangian is basically constructed as a conormal bundle to the knot. And this Gromov-Witten potential encodes in it the geometry of the quantum moduli space of this brane. So just to give you some examples, well, the simplest knot you can take is the unknot. Okay? And in this case, the quantum moduli space is in fact just the Riemann surface derived by Hori and Vafa as capturing the geometry of the mirror. But unknot is not special from this perspective. So you can take the Trefel knot instead, and you get a different answers. So these are Riemann surfaces here P and X vary, and they depend on one complex parameter Q, which is mirrored to the size of the S2 of the P1 in X. Okay. So there are some complicated curves, but look more and more complicated, the more complicated knot you take. So for a figure 8 knot, you get something like this. Now, if this generalization of SYZ conjecture is true, one of its implication is that the closed string theory, the closed B model in all these Calabi-Yau manifolds is the same. And you can show this, so far this has been done for torus knots at genus 0. Okay. And, okay, so far we focused on mirror symmetry. But let's consider implications for transhumance theory and knot theory. Okay, now the Riemann surfaces that arise in this way, if you specialize to Q is equal to 1, they in fact contain the SL2C character variety of the knot as a factor. So that's a moduli space of SL2C, flat SL2C connection on the knot complement in S3. And that fact connects this story to the work of Gukov and Digraph and Dimofta, Sulkovsky, Fuji, and others on the volume conjecture and its generalizations. At Q is equal to 1, so you get this degenerate Riemann surface, which has at least 2 factors, sometimes more. The interpretation of this is that you get actually, of the 2 components, is that you get actually 2 distinct fillings of the same Lagrangian at infinity. One corresponds to conormal of the knot, where P vanishes, and in fact for Q is equal to 1, it's identically 0. And the other one corresponding to the knot complement, where you get the classical A polynomial. So here P and X, so the infinity of the Lagrangian is a torus, and there are 2 holonomies around this torus. One is a holonomy around its longitude, which gets related to X, and the other one holonomy around the meridian, which is P. So the Riemann surface, and at Q is equal to 0, the 2 branches are smoothly connected together. So, so the mirror Riemann surface for arbitrary Q actually has in it information about which cycles of the Lagrangian get filled in the interior. And you get a kind of a topology changing transition which is completely smooth, just in a Lagrangian, not in a Calabi-Yau, but in a Lagrangian. Which cycle changes, which cycle gets filled in changes as you move around the Riemann surface. Okay, but the main application I have in mind is somewhat different. So what we've done so far is we've translated, using large N duality and mirror symmetry, the problem of computing transhumance knot invariance associated to a given knot K, to computing amplitudes of topological B model on this Calabi-Yau Y together with some branes. Calabi-Yau mirror to the knot. This mirror symmetry associated to the knot. Now, if you take a smooth Calabi-Yau, then its B model invariants are determined essentially uniquely from classical geometry of the manifold. For Calabi-Yau manifolds of this type, the geometry in question is the geometry of this mirror Riemann surface, together with a finite set of data, the choice of periods of the Riemann surface, the marking, the A versus the B cycle, a point on the Riemann surface, if you're interested in studying open string invariants or D-branes, and a local coordinate at that point. But this data, once you're given it, it determines all the quantum invariants. There is no additional information for the purposes of distinguishing manifolds with branes beyond that encoded in this classical geometry. Now, huh?
Is it the non-perturbative street coupling or
perturbative?
It's formal.
Yeah. Now, in the present case, all the Calabi-Yau manifolds that you get associated to more complicated knots are actually singular. So with that, you need to do additional work in defining what you mean by the quantum theory on this. But that doesn't change the fact that the composition of two string dualities, this large N duality and mirror symmetry, implies that once you can actually define the quantum theory on this, all transhumance invariants of the knot should be extractable from the B model on this Calabi-Yau. So this gives you a very different perspective on knot invariance than one is used to. Here, it's just this classical data of the mirror that plays the central role. So what happened here, as I said, a result of two string dualities, large N duality and mirror symmetry, that translates computing SUN transhumance invariance on S3 with the knot K to studying topological B model on the mirror associated with the knot plus a mirror brane. So what these dualities do, large N duality sums up infinite number of Feynman diagrams of transhumance theory, all planar graphs, to give you the A model on X to push you through the transition. And then mirror symmetry sums up all disk diagrams to get you the mirror. So, so this machine sums up infinite number of quantum corrections in transhumance theory, and is a better starting point. So that's why it could be a better starting point. Okay. Now, so the way we found these new mirrors is very roundabout. We kind of use transhumance theory to solve Gromov-Witten theory. It turns out that there is a much better way that doesn't involve using large N duality and understanding, if you're just interested in understanding branes on this Calabi-Yau. And I want to describe that. So, I mean, it sounds roundabout that, I want to use transhumance theory to learn something about transhumance theory. It's non-trivial, but still it's roundabout. There's actually a direct way of performing mirror symmetry in the framework of knot contact homology, which lives on the boundary of this of the conifold. Okay, so what's that? I can just give a sketch at best. So this knot contact homology is part of approach to counting holomorphic curves pioneered by Eli Ashberg and Giventhal, which goes under the name of symplectic field theory. And its open version, knot contact homology, was developed by Lenny Yang, and it's designed just for this context, for this conifold with for the conifold. So what it does is associates to X and a Lagrangian in it, or actually more precisely, you studied the infinity of the manifold, where X looks just like R times S2 times S3, that's its infinity, and the Lagrangian looks like R times a torus that hugs the knot. Okay. So you study the infinity of this, and I'll call this torus lambda. And from this data, you get an algebra with a differential. The algebra is generated by open strings that begin and end on the Lagrangian. And more precisely, the infinity is actually a contact manifold. With it, you get contact structure and a Reeb vector field. And the generators of the algebra are Reeb chords. They are open strings that begin and end, that begin and end on the Lagrangian, but lie along the Reeb flows. Okay. So it's the algebra has a differential, which would have annihilated the chords were it not for disk instantons. So the instantons correct this to something like this, whose interpretation is the following. This is counting holomorphic disks with boundaries on the with one boundary on the REAP chord you're interested in, that's at infinity, and other boundaries deep in the interior if you go down towards where the P1 was. And the coefficients are the count of disk in the homology class captured by in the second relative homology class with these boundary conditions. So it's a huge big algebra. A small byproduct of this algebra is its augmentation variety. And for every point in this variety, the algebra has a trivial one-dimensional representation where this BRST operator just annihilates all the REAP chords. And that can be identified with the moduli space of the brain. So again, X and P have to do with holonomies of this torus at infinity along the longitude and its meridian. And Q counts the number of times you wrap the S2. Okay. All right. So this augmentation variety, now this automatically sums up holomorphic disks ending on X and LK, or more precisely the infinity. And now this is not precisely Gromov-Witten theory, but you might think that any way of counting holomorphic curves should give you the same answer. And one can, in fact, show that for P and X in the augmentation variety, P ends up counting the number of holomorphic disks with one marked point, hence the derivative, ending on the Lagrangian and bounding the cycle corresponding to X. So according to this formula. Okay. All right. Now consider higher dimensional. Now suppose we consider links. There's not contact homology is a very precise machine, very effective machine to turn any that can deal with any knots and links and what have you. So in this case, the augmentation variety, which captures the moduli space, is, well, it's naturally a k-dimensional manifold. And in fact, it turns out to be a k-dimensional Lagrangian submanifold of C to the 2k. So C to the 2k simply comes from taking holonomies along the longitude and the meridians of all the knot components. If they're k knot components, there are 2k of these. But the fact that they live in the moduli space relates them and gives you a Lagrangian submanifold, which is Lagrangian with respect to this holomorphic symplectic form. Now, it turns out that if you study links, the varieties that you get are reducible, and there's actually a pretty geometry in this, where the components of the variety that you get actually get related to the number of ways of partitioning the link into irreducible sublinks. So here I start with some link corresponding to 3 knotted knots, and you can pull off any one of the 3 components, and you still get, so these are irreducible links that you can get by that, and then you can further pull them apart. And so for every one of these, you actually get a component of the augmentation variety. Different components, so in this, what the meaning is that they actually correspond to different. You should remember, knot contact homology lives at infinity. So a priori, it doesn't know anything about a filling, or more precisely, it actually knows everything. So it knows about all the possible ways of filling in the infinity in the interior. So for each component of the augmentation variety, you get, and each way of partitioning the link into sublinks, you get a different Lagrangian submanifold of X, corresponding to different ways of filling it in, where the partitions keep track of connectivity. And the A model disk potential of this filling in X is the generating function for the corresponding component of the augmentation variety.
Do all the different components have the same dimension?
They all have the same dimension, yes. Yeah. Now, from Trans-Simon's perspective, the different fillings correspond to different classical saddle points of the Trans-Simon's path integral on S3 with the link. More precisely, I think just to answer your question, I think there are also some components of lower dimension, but they don't actually have any geometric meaning. They're sort of accidental. Okay, so it's only the half-dimension components that actually are meaningful. Okay, so from Trans-Simon's perspective, again, Trans-Simon's theory knows only about the link and nothing about any choices of Lagrangians and so forth. So the different fillings correspond to different classical saddle points of the Trans-Simon's path integral in the S3 with the link. Okay. All right. Now, so I want to talk about something slightly different now, which will get connected back to links in a moment. Well, mirror symmetry, and that has to do with a different way of thinking about this problem. Mirror symmetry relates quantum geometry of A model on X to classical geometry of the B model on Y, but you still get fully quantum theories at all on both sides. You have to deal with string loops parameterized by lambda. The dual perspective I'm going to tell you about is a theory which, in some sense, is maximally classical. Okay, and I'll explain. It's been known since 2003 that if you study B model on one of these Calabi-Yaos that are captured by Riemann surfaces, this theory can be solved completely. And when you solve it, you find that it has a reformulation in terms of a single chiral fermion that lives on the Riemann surface. Okay? So however, it's not a free CFT. Well, it's a free fermion, it's not a free CFT. It's not free in that acting on psi, x and p do not commute. And the lack of commutativity is captured by the string counting, by the loop counting parameter lambda. So this is a bit weird, but it's definitely true. It's weird because it's not what you thought if you started out studying the B model. Now we understand that this result is a consequence of a new duality to where the dual theory is called the D model, which is dual to all of these, but is most closely related to the B model. And we call this, I don't know, lack of a better name, D mirror. Okay, so what's this D model? The D model is actually a model topological string. So it's not telling you about new topological string. It's the old topological string, but in a very different setting than what we are used to studying in. So to quantize this Calabi-Yau, who is captured by a Riemann surface, one starts with, it's dual. One starts with C2 with coordinates x and p, and symplectic form, imaginary part of dp dx, together with two kinds of A-branes. One of these branes is a Lagrangian A-brane wrapping the Riemann surface. This is Lagrangian with respect to this symplectic form. This restricted only vanishes. And the other brane is more exotic. It's the brain which Kapustin and all have discovered in the A model, the coisotropic brain. And this particular coisotropic brain is very canonical, and it's been studied by Kapustin and Witten in the context of geometric Langlands. So this coisotropic brain wraps all of them, the space where this Riemann surface lives, and has on it a canonical choice of flux, so that F plus the symplectic form as just combines to dpdx. Something happened here. Now, the fermion psi arises as the ground state of a string that stretches between the Lagrangian brain and the coisotropic brain. The zero modes of that string are supported on the Lagrangian, on the Riemann surface, and it turns out to be a fermion. Moreover, that fermion provides a module for strings that begin and end on the coisotropic brain. And these strings, as Witten and Kapustin showed, generate a Weyl algebra, which you get by taking functions on M and then deforming by lambda. But in the context of A model, lambda is something like alpha prime, right? It's related to the characteristic size of the string. No, it's not a quantum parameter. And in fact, the modules that arise in this way are holonomic D modules. This connection with D modules has been noted first in the work by Diagraph, Holland, Sulkowski, and Waffa, and then was connected to this work of Kapustin and Witten by Waffa. Okay. Now, this D model is in fact more general than either the it's more general than either the A model or the B model, and it readily extends to higher dimensional varieties. Okay. Usually, we are not interested in B model or A model and higher dimensional Calabi-Yau's because all the interesting amplitudes vanish. It's true here as well that the theory is exact actually at the level of the disk and the annulus, just because it lives in hyperchiral manifolds. But nevertheless, it captures all the information, or it should capture all the information about the B model on the mirror of these historic Calabi-Yau's. But then you can just as well extend it to higher dimensions as well. Okay, and in all cases, lambda just enters as a classical parameter.
Right, what you just said, when you said Lagrangians and high Kähler, do you mean complex Lagrangians?
They're complex, that's right. That's right. So this always gets equipped by holomorphic symplectic form, and these are Lagrangian with respect to this holomorphic symplectic form. So dpdx, in this case that we started with, so the Lagrangian is Lagrangian with respect to that. Okay. Okay, so we can now apply it to augmentation varieties associated to links. This certainly unifies the links and the knots in a single picture, and it's natural to think that D model on this higher dimensional manifold where the augmentation variety lives provides the quantization of the augmentation variety that should be computing the quantum transimus invariance of the link. So in this way, the knots and links are unified in one picture. Okay. One consequence of this, this would in particular, the story would in particular imply the theorem of Garoufalidis that the Helmholtz polynomial of a link is Q holonomic. The story of the D model naturally leads to holonomic D modules, and this will be just one of its consequences. Okay. All right. So let me just summarize the sort of three different ideas in this talk. They're all very conjectural, even for a physicist, but I think they're very interesting. So one is that SYZ perspective, or its generalization, allows manifolds to have more than one mirror. And for the case of conifold, just a small extension of the SYZ ideas suggests that there could be as many mirrors as knots in S3. Secondly, the augmentation variety, which essentially performs mirror symmetry for it, sums up all the disk instantons for both knots and the links, should play a central role in this program of finding good knot and link invariants. And finally, the D model, or rather the A model topological string in this somewhat funny setting of hyperkähler manifolds, should provide a very powerful viewpoint on topological string theory. And I think it's going to play on, well, we already know that it's important in the Langlands, and I think it's going to play a central role in many other problems in mathematical physics. Okay, so thank you.
We have time for questions.
Yes.
So what you're referring to as more than one mirror, isn't it possible to just base this as moduli spaces of different BPS states in one fixed mirror, one fixed ghost string background?
You can think about it like that. But, this could have happened to Strominger, Yau, and Zaslov as well. And in some cases it does. If you study some simple Calabi-Yau manifolds, compact Calabi-Yaus, you can find that there's more than one T3 fibration. And you'd say, okay, so which, of course, you should be able to describe, perhaps, well, you should be able to describe all the branes of the theory in any one of the pictures. But the statement is that there's more than one picture. Right? And that in some sense, these different mirrors are ideally suited to one specific brane. It's the perspective of that brane where the physics of that brane and geometry that that brane sees is described the best. Okay? It should still be true that, mirrors of all that in any fixed frame, in any fixed mirror, you have all the possible branes. Yes?
If you have multiple mirrors, do you get something like a mirror group? You take the relationship between all the mirrors, like in T-duality, you have an ODD. Mm-hmm. And is there an analogous mirror group?
I do not know. Do you have an idea what it might be? I don't know. Yes?
So we know that the topological string computes sometimes quantity for supersymmetric gauge theory for dimensions.
Yes.
It's usually, so the string complement usually corresponds to the case when epsilon 1 is equal to minus epsilon 2.
Yes.
But this setup with this Google-Quickel setup with CC brane and the Lagrangian brane
Yes.
usually corresponds to the case when epsilon 2 equals to 0 and epsilon 1 is a Planck constant. If you want to map to the topological string context, you have to turn on some additional Planck flux.
I think the usual B model corresponds exactly.
It's this hyperkähler models. Okay.
I know. What I mean is that it's Kapust and Witten setup should be the topological string. And it's true that you have some choices of flux, which get related to turning on refinement parameters, and that's something we're studying with Sergey.
I had a question. So there's one computation, so you have this augmentation polynomial. Like there seems to be two ways you're getting your equations for your curve. One is through this augmentation polynomial, and one is some sort of instanton corrected mirror. How are you doing that computation of the instanton corrected mirror? Because it seems like you would need a whole family of special Lagrangian, a special Lagrangian, and you would even know like distant bound.
So if you're just interested in the, say, Lagrangian brane corresponding to the unknot, right? This story was developed long ago and was studied by both physicists and mathematicians, Melissa Liu and so forth. Right? So those kinds of questions were answered in that setting. But not contact homology automatically just, it's business is counting holomorphic disks. And it starts by counting holomorphic disks and assigns to A branes and the conifold, assigns them a variety which should rightfully be thought of as a mirror variety, as a classical moduli space. And in fact, you can show that that definition of moduli space, which is just naive because that's where all the differentials trivially annihilate the Reeve chord, so it sounds like moduli space. In fact, agrees with the one that you would have gotten from Gromov-Witten theory. In other words, the points in the augmentation variety, at least for knots, the P and X that live in the augmentation variety are related by the potential on the disk of just counting holomorphic curves with a puncture. So that's the relation. I don't know if I answered your question. Okay.
Do we have any other questions? But if not, then
Thank you.